Okay, I think we can start now. So, hello everyone and welcome to another Fenix webinar. This is the second webinar of the Fenix Research Infrastructure webinar series that we are organizing. And this one is on how to exploit ICEI Scalable Computing Services. Our speaker today is Sadaf Alam from the Swiss National Supercomputing Center. And I am Nicoleta Chiapidu from the Barcelona Supercomputing Center, and I'm part of the dissemination team of the ICEI project. I just wanted to let you know that the webinar is being recorded, just in case you would like to ask a question later on and you are going to introduce yourself. So this is to let you know that the webinar is being recorded and it's going to be published afterwards on YouTube and on the Fenix website. And you will be able to ask questions either on the chat function during the webinar, or you can also ask a question out loud at the end of Sadaf's presentation. So I will unmute your microphones at that point and you will be able to make a comment or ask a question, or if you prefer, as I said, you can type it in the chat and Sadaf and I will have a look at it. So I think that's from my side. So we can now go ahead with Sadaf's presentation.
Good afternoon, and if some people are in different time zones, good morning and good evening. My name is Sadaf Alam, and today I'm presenting one of the services of the Fenix infrastructure, namely the Scalable Computing Services. I will go through some high-level details because the limited time, the idea is to enable you to understand what is there and where and how to look for additional information so you can have a very productive usage of resources. So the Scalable Computing Services available as part of the ICEI infrastructure is coming from a supercomputing environment called Piz Daint. And here I have few highlights from a user point of view. First of all, you have to think, even though it's a big supercomputing system, it doesn't have, as I can call it, one personality or one usage scenario. For instance, if I talk about scalable computing services on this platform, which is a hybrid platform and a heterogeneous platform, because it not only has GPU accelerated nodes and multi-core nodes, but also different combination of memory configurations. And to the ICEI communities, all these resources are available to be used inside this ecosystem with a very fast interconnect. Another type of ICEI services, which if you followed previous webinar or Fenix website, is called Interactive Computing Services. This platform is designed to offer a subset of those services where potentially people can have a different interface, whether it's in form of visualization applications or an interactive work environment such as Jupyter Hub. By and large, this environment is like any conventional Linux clustered environment. And by and large, when I go through the details, you will see the commonly used tools which are used across the scientific community or code development communities across the world. The Slurm cluster configurations, even though they have some specific details, but they are as conventional as you could imagine in any Slurm configuration environment for running your applications and jobs. Moreover, it has common storage interfaces, as one would imagine from a high performance computing environment, namely the scalable storage interfaces in order to support large scalable jobs, as well as file transfer services within the data center environment and outside. Last but not the least, in order to support a wide range of HPC data science applications and frameworks, there is a HPC container services that are provided there for people to run seamlessly across different environments, from laptop to supercomputing environment. As you get access to the system and as you start consuming resources, one thing that you often find, or a user often find useful, is to figure out how much do I have, how much did I use, who is using my resources. And there are tools, both command line as well as graphic user management environment that you can use once you have access to the system. So before I go into detail, just some highlights overall how the system or the environment looked like. So from an infrastructure point of view, the vendor that built Piz Daint is Cray. And because it's a hybrid and heterogeneous system, it has two types of, you can call them partitions, but they are under the same high-speed network environment. So essentially, from a Linux cluster environment point of view, although the model from Cray seems different simply because of the size of the blades and cabinets, from a user point of view is one system. But if you are interested in these details from a model OEM model point of view, this is how one would define a Piz Daint. And now you see the distinction. An XC50 compute node is composed of an Intel Xeon processor, 12 core, it's DDR memory, and an NVIDIA Tesla GPUs. Altogether, there are 5,704 such nodes available on the system. The multi-core nodes are the next generation Xeon processors with 18 cores per socket, or 36 cores in total, or times 2 threads. And there are two types of memories. Such memory nodes are available. Altogether, there are 1,813 such nodes. You access the system or these compute resources through something we call login node or front-end nodes, where you have all the compiler, build, job running environment. And these are the details of those nodes. It has a high speed, high bandwidth global interconnect, which is quite essential for especially low latency, high bandwidth workload, primarily written using message passing library like MPI. And in this case, the network interface is proprietary from Cray called Aries, and then the topology is Dragonfly. And it has a scratch capacity of usable 8.8 petabytes. So now moving to how do I bring my applications to the system. As I mentioned before, it has a very conventional programming environment, whether you are a Fortran programmer, C or C++. And all these compiler options is available with OpenMP and multi-threading support. So the compiler options you have are Cray compilers for all these languages, Intel compiler, if you like using them for your current applications and environment, GNU environment, and PGI. I'll go a little bit in detail about one or the other, but the important thing to remember here is you have most commonly supported programming models and environment by multiple vendors. The MPI library has a standard MPICH interface, like a standard MPI library interface. However, it is optimized for the Cray proprietary networking environment. But this optimization is usually transparent to most users, but there are options in case someone wants to tune and optimize applications further. Of course, there are GPUs, NVIDIA GPUs, so it comes with NVIDIA tool chains, which are highly integrated in Cray, GNU, and PGI environment. And in addition, you have a PGI OpenACC compiler. And typically, this version is kept up to date. Last but not the least, there are libraries for supporting scalable applications and workloads. And these include numerical libraries, for example, for dense matrix operations or PETC, fast Fourier transform, as well as parallel IO libraries like NetCDF and HDF. So as a highlight, I added some details here where you can go on CSCS website and from when you enter the system, if you specify which type of environment you want, namely for GPU or multi-core, you will get one default version, a complete default version of one of these. Because it's a heterogeneous and large-scale system for multiple users, it's important to understand how resource management and scheduling is done once you have an application or a code ready to run. Slurm is the batch scheduling system on Piz Daint, and the type or excess of resources in terms of the number of nodes and the type of usage is divided into different queues. So if I go one by one, so there is a debug queue. As you can imagine, as the name suggests, when you are debugging and troubleshooting a piece of code, you probably don't want to sit through a bad job while you are more or less working in an interactive mode. But because of this quick turnaround time for test jobs, one per user, so that is not exploited, it's limited in terms of number of nodes and the length of time. Then very often than not, there are reasons where people would like to run larger jobs. And because of such a large system and the effect of what we call draining the nodes to make a space for large scale jobs, we prefer that these are done in consultation with the support staff. There is a long queue again because it has a special feature, namely the length of time you have relative to the normal queue, namely 72 hours versus 24 hours. It has some constraints, such as the one listed here, maximum 5 jobs in total, 1 per user. Normal queue is by far the most commonly used queue among all the users, and it is designed so it provides a fair usage of the system to all users and all users' needs. So the length is 24 hours job length, and it is designed for production work. It has some constraints, namely what you see here, that maximum you can ask for 2400 GPUs and 512 for multi-core. And with the special arrangements, of course, you can ask for more, but this is by far the workhorse queue of the system. And the last two queues are to support workflows, pre and post-processing queue in order to make sure your workflows progress through the system quickly, and transfer queue for data staging so that you don't end up using your compute node hour allocation to stage in and stage out your files. A little bit more later on this topic. So Piz Daint by far mainly is a compute system, but it has a lot of peripheral or important storage and data transfer services to make users work very productive. And these are defined into different types of file systems. And these file systems have performance characteristics because we would like to be able to support large scalable jobs. But at the same time, depending on how people would like to store and process their simulation output, some of these systems have functional characteristics. So I will go through some of them because this information again is available online. And then there is a data transfer service. There are data transfer services where I'll go into detail, where you have to stage in and stage out data from internal and external file systems to support your workflow. So for the scalable compute services, the main system or main file system is a Scratch file system. As the name suggests, it's a Scratch. So the idea is it can support large scalable jobs running on multiple on nodes, so that your performance is not limited by the performance of the file system. The type in terms of a parallel POSIX file system is called cluster. There is no quota in terms of capacity, but there is quota in terms of how many small files a user can have in terms of inodes. And this quota is enforced because the performance of cluster could be quite adversely affected from a large number of small files in the system. There is an expiration of 30 days, and in some cases it can also depend on the how full the file system is, so that the performance doesn't drop for most users. There is no backup of your data, as the name suggests, it's a Scratch. It's fast. We have numbers we can list, like theoretical peak is 100 some gigabytes per second, and the capacity is there. I will skip the Scratch clusters because this is not applicable for this presentation. But then you have users and project and store file system, which provide capacity, but not the same type of performance as a Scratch. And they serve different users. So for instance, the user is where user primary information is a GPFS file system. It has an enforced quota and files and some backup properties. And so the project is the file system where you would like to keep your stage in and stage out data. And it has, again, a limit depending on the project, and you have a timeline how long you can keep the file system there. And I will skip store because it's an additional services that are offered to projects, but it has virtually similar characteristics as project. In order to support multiple workloads and software integration deployment processes, at CSCS, we have been working on container services for large-scale Linux cluster operation, because containers is not something new to the community. And largely, we have two such solutions. One is the local one, namely Saurus. And then the most commonly used HPC one is Singularity. Here, I will only mention Saurus on how it is deployed and used in the system. So it's a software for running Linux container. So the idea is the container build process is similar to like any other Docker compatible image build process. It is security oriented in terms of access to shared resources such as file system on an HPC environment such as Piz Daint. It is compatible with Open Container Initiative standards, so you can plug in other resources such as GPUs and other accelerators in a standard way, or exploit those plugins. It is integrated with the workload manager, namely the Slurm resource management and scheduling system. And it is designed so that it works with diskless nodes, because none of the compute nodes on Piz Daint have any local disks and parallel file system. So that's how it differentiates from a conventional Linux container environment. And there is link for details, but the usage, like in any other user level software tool, is you go to the environment you would like to be, whether Daint GPU and CPU, you load this environment, and the rest of the steps you can follow from the instructions. Now I focus a little bit about the scaling aspects of Piz Daint and where we provide specific or specialist tools for debugging and performance analysis and some frameworks. So for debugging and performance analysis at scale, and there is a link there, we have to consider multiple aspects. One is we have to provide tools that work on the multi-core part, as well as GPU together with NPI. So majority of tools you will find available, they do not cover the full spectrum. And in Piz Daint, because of its hybrid and heterogeneous features and characteristics, if you are building applications in multi-core environment and GPU environment, you will have tools available and scalable tools available to debug your code, namely with this linear DDT tool. And for GPU, for GPU code developers who are familiar with NVIDIA toolchain, those tools are available as well. For performance measurement, analysis, and debugging, again on multi-core GPU and MPI, there are a set of gray performance tools called perf tools. There is this tool chain by the team led by Dresden, Vampire, Scorpio, and Scalaska, and NVIDIA performance tools for experienced and proficient users of NVIDIA toolchain. And all these details are available, as I said, in the links below. There has been a lot of work going on in the past few years in making sure the data science frameworks, which are historically designed for systems that do not quite look like Piz Daint, namely diskless not with direct access and with MPI, efforts are being ongoing to make sure these environments are available for users, again for multi-core GPU and MPI enabled form. And some of these frameworks include up-to-date versions of Python and its libraries, TensorFlow, Theano, Spark, and Task. And they can be exploited on the system once you have access on the system. I say a little bit about interactive computing services because this talk is more about scalable computing services. So I would like to just mention that there are multiple ways to access such resources. And here what you see is a Jupyter Hub service at CSCS. When you go there, you can see Jupyter servers on demand for users on Piz Daint. Again, there is a limit. So once you have a CSCS account, you go and access there with the credential. You can choose what type of dedicated node access you want. The launch time should be limited because this still has to go through some resource management and scheduling pipelines, but it's not batch for if you are asking for single node jobs. And then you have further details to customize your environment. So this was for me a little bit background to what is Piz Daint. And I have a few slides to go through to explain how to do certain things. And again, this how is like the explanation of Piz Daint is high level, or rather high level. And the hope we have is that for the users of Fenix and ICEI Scalable Computing Services, you have sufficient information to get started and to be productive soon. So at the first step, anyone accessing Piz Daint is to make sure they have a valid account. And I added some links here, which are specific to CSCS, not specific to Fenix and ICEI, but you can get a feeling for processes. and the Fenix details are separately provided in the project. And then, assuming you have an account, you have multiple ways to find out what is your username, which project you belong, how much quota you have, etc., or access to resources. So you can access these services via browser, assuming you have a valid allocation or grant. You do not directly go to Piz Daint because for certain reasons there are services in different security domains. So there is a service we call ELA. You can consider it a front-end service or external login interface to a login interface to an HPC system. It may sound complicated, but it's pretty straightforward. But this environment, which kind of redirects you to Piz Daint or other cluster environments with CSCS, it has a minimal Linux environment. So once, assuming you have an account and you have access to CSCS resources, you will SSH ELA, and then you go to Piz Daint from there. And you will probably start doing some file transfers before you do work. It's not essential, but that could be one of the steps. And then you can follow the instructions about transferring files from outside CSCS environment. One thing to note there, because it's a minimalistic environment and it is not equipped with any programming environment and tool, and it cannot see all file systems either. So the amount of work you can do on the front end is quite limited. Assuming that you are on Piz Daint and you would like to compile your code, the environment is based on a module, very standard module-based environment, if anyone is familiar with it. So once you access Piz Daint, and assuming you know whether you want to use the GPU part of Piz Daint or multi-core part of Piz Daint, you will do a module list. And typically that gives you a preset environment or a default environment for the given pieces of the resources, namely Haswell and NVIDIA Pascal GPUs or Broadwell multi-core GPUs. And then you can use standard commands for other tools and applications such as module avail, or if you want to change something, you can use module swap. The unique aspect here or in a Cray environment is that it provides wrappers for different compilers. And these wrappers set a lot of default environments. So for any HPC user, this is one of the things they like most about the environment. So they do not have to worry about linking to the proper MPI library or any maths library. There are a lot of default options set as part of this wrapper. And regardless of whether you are using Cray, Intel, or PGI, you will use CC as a wrapper for C code, the uppercase CC for C++, and Fortran for Fortran code. Of course, there are other flags, and I strongly encourage, if you are not familiar with the Cray environment, to just do a man page or a search for these things. But this is very powerful feature for majority of HPC application teams, because out of the box, you can compile and you can run in a scalable environment without worrying about whether my default library paths are set for compilation and execution. Of course, because it's a GPU environment, you have an additional option which is not mentioned here, which is directly by default uploaded when you do Daint GPU, is setting of all NVIDIA libraries, as well as if someone who is interested in doing directive-based programming like OpenACC, those environments are set for you for default. So for majority of users, if they know whether they like GNU, Intel, or any other compiler, and they want to get going, and they have their application environment set up in a clustered environment, this step should be very, very straightforward, because of a lot of complexities of the environment has been hidden behind these wrappers. Assuming you have successful in building your applications, or you have something to run, you go to Slurm. Again, for new users, you may want to familiarize yourself how a job script is written and how to submit a job. But any user who is familiar with any job submission environment, you can find it very straightforward to use your existing job scripts, especially if you come from a Slurm type of environment. Of course, there are a few things you may have to pay attention to, such as the type of partition you want to use or the constraint, meaning that GPU or multi-core. But other than that, you use typical SRAM program and your code should be able to run through an S-batch. At CSCS, and I provided a link there, there is a Slurm JavaScript generator, which you can use to fill out your details, and then it will provide you something that once you have it, you are ready to go. While your application is running, you may be interested in certain things. Is it running? Where is it? Which status it is? And what is the status of different queues, for instance? Again, if you are familiar with Slurm or any other job scheduling environment, you can take these things for granted. If not, then you can very quickly look up for information, and almost all Slurm commands will work as they work in any other cluster environment. So your data is a very important part of your simulation and job before and after. So data stage in and stage out services are part of the productive usage of the system. So we have data and storage orchestration services. So one thing is transfer queue. And this is primarily to address data transfers between internal CSCS file systems. And there is an example written there on how to use it. One thing to remember that this queue is been created like this just to make sure that you do not have to worry about consuming your node hours for scalable compute services here. And the Slurm queue to manage this is completely integrated to Piz Daint cluster environment. So you can create a dependency and you know for sure that until your data is there, the job won't start. If you're coming from outside CSCS, we have a classic grid FTP type of transfer service with Globus, as well as support for Fenix archival data repositories through a OpenStack Swift API there. I do not provide details here because the emphasis and focus here is on the usage of scalable compute services. So the hope and expectation is everything works out of the box and job gets done quickly. But let's say if you run into situation at first step, at second step, at nth step, what do you do? There are multiple things to do because the nature of what you are troubleshooting could vary a lot. First thing I would suggest is to look at some of the frequently asked questions. And I provide a link there. And your question may or may not be answer to your question may or may not be there. And then there are other steps to follow, which I will mention later. The second thing is if you are in full code tuning, development, and execution mode, you can be in a situation where you could have correctness issues, performance issues, scaling out issues. I put a picture of a code called Alinea DDT. And the tools you have on Piz Daint not only help you in debugging your application at scale. For instance, let's say you run your application on 10 nodes, it ran fine and gave correct answer, but when you ran it on 100 nodes, it gave a wrong answer, or it crashed. You would like to be able to figure out and find out where and how, and these tools help you in that. Same way for performance. If you ran something on 4 GPUs and then you run it on 8 GPUs and it runs slower, you would like to really understand whether the issue is coming from GPU communication, MPI communication, or a combination of these. And there are tools that can help you in highlighting where the sources of slowdown, imbalance are coming from. So these tools are there and they are routinely used by the users on the system as they exploit these scalable computing resources on the machine. So once you have a computing budget granted to your project, you have some command lines tool like SPU check, which reports group usage across various computing CSCS systems, and it provides you this information. What is the quota? How much have you used? Because the way we give out quota on Piz Daint is specific, that every quarter you have a limit to use the quota in that quarter. You can also look at the usage per group and group member. And in addition, you have a browser-based tool, we call it User Management Portal, where you can go in and depending on your role, whether you are a principal investigator or a user, you can see different types of information of not only scalable computing resource usage, but also storage and others. Just for your reference, because the title of the presentation is usage of Piz Daint for neuroscience, and I provided you primarily usage of Piz Daint. And there are indeed projects, the human brain projects, that have ICEI allocation running on Piz Daint, and a list of these projects is provided here, and the link to the press release covering, and there are more now, are available for your reference. And these are there, so in case you have any comments or question, or you see some PI you recognize or some tool you recognize, you can then reach out and make a productive use of the system already. I included, because these slides will be distributed, a link to references, because in my slide, I refer to a lot of information that is definitely not self-contained, that is not part of this presentation or slide deck alone. Of course, the first step is you would like to go and find out what resources are available through Fenix Research Infrastructure. And there is a list of not only scalable computing resources at CSCS, but other resources that are already online or soon to be coming online. One important source of information is CSCS user portal, where you can navigate and find information on if you need some existing application and tool chain. If you're very keen on finding what comprises Piz Daint in terms of its hardware specifications, you can go to this link, which was published some time ago, but you can definitely use it as a reference. And CSCS holds something called user lab days. And in fact, I use some material from those days, one of those things. So you can go to this slide and then you can find various presentations on different topics where I didn't go into details, but those presentations went into details. So I would encourage you to have a look there. There are training events for Piz Daint and related ecosystems, software ecosystem and frameworks and tools. You can check them out, and you can go to previous ones where typically you have links to the material that was presented at those workshops. Last but not the least, CSCS maintains what we call it a service catalog. It is more than Piz Daint, but majority of services, especially the application level or data science framework services, are almost exclusively available on Piz Daint. So you can go and have a look there if there is a library or there is an application or a tool that you are interested in, because it will be available to you if it is listed there. If there are any questions, I have a link to how to contact us afterwards. There was a webinar before, including this one, that will be presented there. And as I mentioned, if you are keen on, which I hope you do, asking for resources, you can find details through the last link.
So I would just like to thank Sadaf one more time for her presentation, and to thank our partners for making this happen, this webinar series. I would like to announce our next webinar, which is taking place on Tuesday, 28th of January at 3 o'clock again, and the topic will be guidance on how to submit applications to use the Fenix infrastructure. More details about this will be announced on the Fenix website and Twitter account very soon. I would also like to let you know of our email address. You can send any comments or questions to the email address that you see here. You can be up to date with all the Fenix activities by checking our website and also our Twitter account. I would also like to ask you to please complete our post-webinar survey that will be sent to you tomorrow. So that would be very helpful for us in order to improve our next training activities, but also to provide you with support with using the Fenix services. And I would like to thank you all very much for attending this webinar. And the full recording will be available on the Fenix website very soon, and you will all be informed. So thank you very much and see you soon.